the biggest misconception about the sun is people think that it doesn't do anything. They think it's just like constant, unchanging, it's the same one day as it is the next, but that is just not true. The sun is constantly changing, churning, day to day, week to week. There's always something different happening on the sun.
Welcome to the Aviation Show, brought to you in association with the Pima Air and Space Museum. Hello, Ryan. Thank you so much for joining us. We've got a lot to get through today. For our viewers and listeners, do you want to just do a quick bio? Because you've got a fantastic job and a fantastic title. So tell us a little bit about yourself.
Absolutely, Matt. Yeah, thank you for having me. So my name is Ryan. My main job is I'm a solar astrophysicist. So my day job is I use telescopes in space, telescopes on the ground. I analyze these explosive events on the sun called solar flares, essentially just trying to understand what a flare is, why they happen, when they do, how we can ultimately predict them. And then sort of beyond the day research job, I also love communicating the science of the sun and space with listeners, viewers, readers, whoever will pay attention to me. So I've written a book last year called Space Hazards, which I know we're going to be talking about today. But I also post about the sun nonstop on social media and things like that too.
Yeah, we'll put all your socials in the description because they're fascinating. This sun is a beautiful, beautiful thing. And it's always nice for you to post something and say, our mobile phones won't be working in 2 days. Everybody get ready. So yeah.
It's crazy. I think, the biggest misconception about the sun is people think that it doesn't do anything. They think it's just like constant, unchanging, it's the same one day as it is the next, but that is just not true. The sun is constantly changing, churning, day to day, week to week. There's always something different happening on the sun. And I try and share sort of the most beautiful and relevant, we'll say, for reasons that we'll talk about in this podcast, I'm sure, the most relevant and beautiful of those events on the sun.
Brilliant. I'm delighted we finally got to do this because we've been going back and forth on this for a while, and mostly that is me totally ghosting you, so I apologize for that.
But you're forgiven. We made it happen.
Thank you. That's great. So what is the idea behind Space Hazards? Because you cover a lot. We're going to look at 2 or 3 things from the book today, but what was the idea of putting the book together with the Royal Observatory at Greenwich, which is also on the cover?
Yeah. Great question. So it all started with the sun. So I talk about the sun a lot in my research, of course, and I do public talks and things. And I quite often tell people about the influence that the sun can have on our society. So we'll talk about some of these in a little bit, but the sun and activity on the sun can influence our power grids, our sort of aviation sector, satellites, networks, all of these things. And so I thought it would be a good idea to sort of write a book about this, not from like a strictly scientific perspective, but almost from like a society perspective. Like, why does it matter? Why do we care? Let's pretend for a moment that we don't care about astronomy, which we all should, right? But even if we don't, 100%. Like, why does it matter? So it started off with the sun. And then as I began to put the book together, I thought, wow, there are definitely other things in space that are very relevant to this topic. So near Earth objects, so comets, asteroids, meteors, these are something as well that we are researching, not just from an academic perspective, but also from a sort of a planetary safety perspective, space junk too. And then I think those are the ones we'll talk about today. But later on in the book, I also talk about really wacky things that are very low probabilities of happening, but could theoretically happen. So what would the impact be of, a rogue black hole passing through the solar system, or what will happen when the sun eventually dies, right? So all of these things are covered from the sort of the now and relevant to the maybe one day, but maybe not sort of categories of space hazards.
It's a lot of fun. And just, you don't want to judge your book by its pictures, but the pictures are gorgeous. You've got a really lovely selection of imagery in the book. Yeah,
you definitely have my permission to judge this book by the cover, because I think it's a nice cover. There's lots of pretty pictures. It's as you say, it's more than just text. So really trying to hammer down the sort of beauty of some of these things too.
Brilliant stuff. So let's get cracking. We're going to start with your specialist subject, the sun.
Yes. Yeah.
And I think the easiest way to start this is, what sort of star is our sun, and how does its behavior sort of start to impact us? Because I think that's a pretty big question, but what type of star is it?
So the sun you can think of as kind of your average star. It's relatively unspectacular in the scheme of stars throughout the galaxy. It's middle-aged, so we're about 4 billion years old, 4.5 billion years old. It will last in its sort of current state for another 4.5 billion years or so, at which point the sun will expand to a red giant. Will kill us all, but that's a long way down the line. I think that's on a Tuesday if you do want to put that in your calendar.
Super.
But for now, the sun is just ticking by. The sun, like all sort of main sequence stars, as we call them, so these are stars on sort of the main track of their life. It is powered by a process in the very core of the sun called nuclear fusion. Now, during this process, you have hydrogen atoms are smashed together. They are smashed together with such pressure and force, they actually sort of are compressed into a helium atom. And that process releases a lot of energy that essentially powers the star. So the sun itself, stars, powered by this process called nuclear fusion. But everything interesting that happens on the sun, at least in my opinion, my professional opinion will say, everything interesting has nothing to do with nuclear fusion, has nothing to do with the core of the star where all this energy is being released. All of the fun stuff happens near the surface, at the surface, and above the surface of the sun. So in these sort of domains, it's not nuclear fusion that dominates, it's actually magnetism. So magnetic fields, electromagnetism, these are the forces that determine the evolution of our sun and the processes that affect us here on Earth. So you might have heard of a term called sunspots. These are just dark spots on the patch of the sun. Sometimes if there's one that's big enough, you can just see it with a pair of eclipse glasses, and that's how big they can get. These are essentially just giant magnets like nestled in the sun's atmosphere, and that the magnetic field is so strong that it like repels plasma from around the sun, and that causes them to sort of be this dark color that we see. But these magnetic fields, they're more than just sort of visibly cool, right? These magnetic fields, they can evolve, they can twist, they can tangle, and they can break. And sort of the breaking of these magnetic fields essentially release colossal amounts of energy. We observe this on Earth as a solar flare. So a solar flare on the sun is just a breaking of energy, a breaking of magnetic fields in the sun's atmosphere, and it releases sort of light, high energy particles, heats up the local environment around the sun. And these can also, not all the time, but a lot of the time, as this is happening, it can also sort of trigger an eruption from the sun. So you can think of your solar flare, if we use like a historical example, right? Let's think of a medieval cannon, for example, right? You light the fuse, you have the bang. That bang is your solar flare. That's your release of energy, your sort of muzzle flash, the sound, the light. And then sometimes, not every time, there's a cannonball loaded in the cannon, and that shoots off into space in this scenario, right? And that is an eruption from the sun that we call in this term a coronal mass ejection, which sounds complicated, right? Coronal mass ejection, but it's just an ejection of mass, so stuff from the sun's atmosphere that we call the corona.
So when we sort of, as the layman sort of say, all that stuff is a solar flare, that's just the kicking out of the mass. And then underneath that, we'll, as we're going to talk about, there's lots of different elements for that. So the coronal mass ejection is one thing. How does that then sort of affect us on its journey to us? Because I guess we see it before we feel it.
Yep. So there are different ways this process can affect us here on Earth. And this colloquially sort of comes under the umbrella of something called space weather, which is how things in space can influence the Earth environment. So I don't mean how it influences our weather here on Earth. I mean how it can influence our sort of near Earth environment around us. So space and then sort of on the ground too. So the sort of three main things that can happen, right? You have your solar flare. This is a burst of energy, a flash of light at the sun. This light is light, so it travels at the speed of light, which is very, very fast, 300,000 kilometers every single second. So that light takes 8 minutes to reach us. And during the solar flare, it produces a lot of X-rays and ultraviolet light, the type of light that we don't see with our eyes. And this actually, as it hits the upper atmosphere of Earth, it can heat up our upper atmosphere, a region of our atmosphere called the ionosphere. Now, this does not heat up the ground or anything like this. It's just heating up this very high altitude layer. But this has a very important consequence for radio communication. So the way we communicate with radio waves, so we communicate from from a plane to the ground, or from the ground to a ship, or from the ground to a satellite, is we use radio waves, and these radio waves sort of bounce off the atmosphere as they sort of travel around the Earth. That's how we're able to communicate over the horizon. And when we have a large solar flare, this doesn't work. The upper atmosphere expands, radio waves no longer bounce off. So your radio communication, or essentially over the horizon radio communication, essentially shuts down. And there are definitely sort of impacts relating to that maybe we can discuss. That's the first part.
I can remember trying to make high frequency radio calls to aircraft when I worked for the airlines, and certain times of the year you just ring Radio Stockholm or BA Speedbird, and they're just like, yep, not going to happen today, I'm afraid. And you have to wait.
It just
for another way.
Yeah. So if you're like in the military, right, and you wanted to sort of do a sensitive operation, or you are doing disaster relief in like a rural area or things like this just shuts down, just stops working. So you really want to check what's going on.
Just to pick up on the ionosphere a bit, because one of the things I want to say is that the Earth is fantastic at defending against most of this. So some of the things we're like talking about with radio things, I guess really it's us that is affected by it, and the Earth does its thing to sort of protect itself. Are the things that we're going to be talking about here really the stuff we've invented that can't cope with this, whereas the Earth, being the Earth, is just a lot better at it than we are?
Yeah, you're certainly right in a way. These three types of space weather, we've talked about one, we'll talk about the other two. The Earth does a fantastic job at defending us, both with its atmosphere, its magnetic field. Does a fantastic job biologically. Our bodies are at no risk, no direct risk to our health, unless you're an astronaut in space. We can talk about that, or if you are on a plane high over the poles, maybe. But on the ground, we're safe, right? So it is not our biological systems that are affected, again, unless you're in those specific situations, but it is our technology. And we do rely on technology. I want to caveat before we go into sort of these effects. Nothing that we're talking about here is apocalyptic. We're not talking world ending, nothing like that. But these largest events that could happen maybe every like 1 to 200 years, these very large events could cause sort of some widespread economic impacts, grounded flights, loss of power, things like this. And those large impacts, those costs could rival the impacts of other very large natural disasters that we've had. But again, this is sort of a 1 to 200 year level. At sort of the smaller level, sort of every decade or so, we still do have impact, and we can discuss some examples today.
Yeah. But you say that, but your last chapter is called "The End of It All." So
yeah,
you do get that at the end.
but I'll caveat that by saying, at the end of it all, we're talking billions of years in the future. So if you're immortal, sure, you can worry about these things, but for now, we're okay.
I was interrupting with a silly joke.
Oh, no. So we have these three types of space weather, right? The first one is light from this solar flare that hits the upper atmosphere of the Earth. The second one that often gets sort of swept under the rug there are very high energy particles, so protons and electrons. These are accelerated by these events. These don't travel to us at the speed of light, but they can reach us sort of minutes after the solar flare arrives. And these can cause some sort of wacky impacts. So first of all, there's the effect on biology. Okay, so if you are in space and these particles sort of fly through you, that is sort of the equivalent of getting a high dose of radiation, right? So radiation, the human body can tolerate some of it, right? Like you go to have an X-ray at the hospital, you have a chest X-ray that gives you radiation, but that's sort of worth that risk, right? Because you're getting a gain from that radiation dosage. But if you're an astronaut in space, you can get exposed to this radiation, and it can add up over time. So if you're in low Earth orbit, so the International Space Station, you are okay. There are sort of protocols in space. The space station is big enough that it can provide you some shielding. If there's a very large event, you don't go outside the space station. You don't go to the laboratory wings. You sort of nestle in the residential quarters in the middle where you have a lot of protection. But if you're an astronaut outside of low Earth orbit, say an astronaut en route to the moon as part of the Artemis missions, for example, you are very, very exposed. And if you are unlucky enough to be in space during a very large event, and there are mitigation plans to try and not put astronauts in space when there's a high risk of these. You could receive very high doses of radiation. It's not going to fry you on the spot or anything like that, but it can lead to increased risk of cancers and things like that throughout your lifetime. So absolutely not something to mess around with. And the same is true in a way for flights. So up near the poles specifically, so at very high latitudes, you are exposed to higher doses of radiation during these events. And so airlines will actually are tied into these forecasts, and they will redirect flights to not fly over the poles if these levels are really high. So they'll push these flights down to low latitudes. Maybe your route is a bit longer, but in exchange, it's okay if you're a passenger because you're just on a flight, however many times a year. But if you're a pilot or crew, you don't want to be repeatedly exposed to those situations.
So we can predict these space weather patterns reasonably well, can we? And I guess the converse of that is sometimes we just get surprised.
Yeah, I think reasonably well is a good colloquial term. There are certainly challenges. So the hardest part is predicting when a flare is going to happen. So we can see these sort of regions on the sun that kind of look kind of gnarly and complex and look like they might do something. But we're not yet at the point where we can say, okay, tomorrow this sunspot on the sun is going to produce this large flare. So we're sort of stuck with sort of probabilistic forecasts like, maybe 1 in 10 days, this region will do something big. But when that flare happens, right, everything that comes after these high energy particles, the coronal mass ejection that we can talk about next, these are more predictable and these take time to reach Earth. So you do have a bit of forewarning. The biggest trouble is not our scientific understanding, it's our lack of data. So if you imagine if I'm the sun right here, right, and you're the Earth, and I produce an eruption of plasma or particles and it's heading towards you, it's very difficult to determine how fast this thing is going. Sort of just, if it comes off at the side, it'll be very easy. You can see, okay, I can see how fast this thing is moving. But when it's coming right at you, which are the events that we care about, it's very difficult to know. So we have some satellites coming up in the next few years that will be sort of offset from this Sun-Earth line to get sort of a side-on view to provide a bit more insight into this. But at the moment, it's pretty challenging. And the last sort of category of space weather that is the most important to forecast are these physical eruptions from the sun. So we talked about coronal mass ejections. These are just huge structures of plasma and magnetic field. They expand very quickly, multiple times the size of the sun, and they travel out through the solar system. These are directional. So they could go, up, down, left, right, away from the Earth or right towards the Earth. And it are these ones that we do care about. But as these eruptions head towards us, again, we talked about the Earth being protected, shielded. We have this big magnetic bubble around us, our magnetic field, without which we would be screwed. But this protects us, right? And this eruption from the sun can basically smack into Earth's magnetic field. It doesn't matter sort of the angle of these as they approach, but as they hit each other, Earth's magnetic field, you can think of kind of like wobbles as it's sort of impacted by this thing from the sun. Sort of certain layers of our magnetic field are sort of stripped back. And as this happens, high energy particles sort of enter our magnetic field. They flow down, they hit the air above us, and the air starts to glow. And so that's the cause of the northern lights and the southern lights, is the air above us glowing as it's getting smacked by these particles sort of from the sun. So there have been some quite high profile events the last sort of 2024 to now. You mentioned you're in the south of England, and I wonder, have you been lucky enough to see the aurora from the south of England any of these past few times?
We've not had them here, annoyingly, but I have spent a lot of time up in Bodø, northern Norway, and I've seen them a few times
absolutely.
up there. It is wondrous, is the only way to describe it. It's just amazing. So bright greens and purples and all kinds of. It is wondrous.
There have been some occasions I know where it has come down to the south of England, but you have to get lucky, sort of being awake at the right time, knowing that it's going to happen. But these are unusual events, right? Normally they don't come this far south. But whilst this is happening, right, as you're seeing these pretty lights in the sky, there is something invisible happening around us at the same time, which is slightly less pretty. So I mentioned as this eruption comes from the sun, smacks the magnetic field, sort of the field sort of wobbles and changes and moves. Now, there's something that sounds very boring in physics, but just bear with me just for a moment, right? It's something called Faraday's law. And Faraday's law says if you have something that conducts electricity, so I don't know, a wire or something, right? You have a cable. If you change the magnetic field around this cable, then electricity will start to flow inside it. This is the principle of wireless charging. If you have like an Apple Watch that you charge wirelessly or use wireless charging for your phone, this is the same thing. You just change the magnetic field, you can create an electric flow without having to be connected. So whilst our Earth is being hit by this thing from the sun, our magnetic field is going crazy, the magnetic field is changing and moving. So what that means is down here on the ground and in space, anything that conducts electricity, this whole process creates sort of a phantom electric signal that is coming from nowhere, right? It's coming from the change in the magnetic field around us. Electricity starts to flow. And this whole process is called a geomagnetic storm, is what we call it. So if you have a power grid, for example, which has electricity flowing through it, now all of a sudden this geomagnetic storm is creating more electricity in your power grid. You can sort of reach levels that overload your systems. So you can damage transformers and you can cause power outages. And there have been some high-profile incidents of this. Back in 2004, power grids in Sweden and South Africa, transformers were damaged and broken, and there were power outages for several days as a result of this process. Back in 1989, there was a very famous example in Canada. So sort of east coast of Canada, there was a hydroelectric plant that the transformers overloaded and broke the system, and they lost power for I think about 15 hours, millions of people without power. So this is one of the larger impacts of this happening. These events, again, these are sort of strong events, but not like the strongest events. The strongest event to happen in recent, I'll say, sort of human record was way back in 1859. So not recent, right? This event we think is maybe like a 1 in 200 year event. It's called the Carrington event. It's named after a man called Richard Carrington, who observed a solar flare on the sun, probably the first ever observation of a solar flare. And then about 16 hours later, Earth was smacked by an eruption from the sun. The northern lights were seen all the way across the Americas, right? It was nighttime there. And then in Europe, the peak of technology at the time were telegraph machines, right? Yeah. And these telegraph machines started receiving just random noise, letters, numbers coming into the receiver. They would turn off the power, the messages would keep coming, they would try and fix it, and they would get electric shocks and sparks would fly. And this was because they were being powered by space, right? They were being powered by space, and they had no idea what was going on. So, you know, our power grids, our telephone lines, railway networks, sort of internet cables, these are all susceptible to this process. But smaller devices like, you know, your phone, or if you have a solar power on your roof powering your house, that's not going to be affected. It's affected mostly by long conductive things that continue for sort of tens and tens of miles. That's where the current builds up the most.
So to wrap this segment up,
yeah,
how are we protecting ourselves against, you know, we can't shield everything. So is it just a trade-off of saying this is going to happen occasionally, we're just going to have to live with it? Or are we trying to devise ways to make our technology less susceptible to this? As you know, we're chatting to you're in Colorado, I'm in England. You know, we kind of need our long distance communication. Otherwise, no one's going to have YouTube anymore. It's going to be terrible.
Yep. We do need long distance communication. And I want to say the worst case scenario, if we have a massive event hit, maybe like a 1 in 200 or 500 year event, we would lose these services perhaps we're talking a few days. We're not talking weeks or months. So maybe, you know, 2 days unplugged could be good for the world. I don't know. But certainly, as you allude to, as our technology improves, we are becoming less susceptible to this. Power grid technology is getting better, for example. But the big thing that we do is prediction. So there are companies or agencies, I should say, around the world. In the USA, there's NOAA, which is sort of the national Oceanic and Atmospheric Administration. In the UK, there's the Met Office, the Meteorological Office, who forecast regular weather. They also forecast space weather. So they look at the sun 24/7. There's someone sat at a desk at all times watching the sun. And when these events happen, they all put out forecasts of those impacts to the relative industries. So if you're in the satellite industry or the aviation industry or the power industry, you will receive notifications when these things are happening and likely. And each industry will have its own protocols to sort of mitigate some of these risks. So using the power grid example, again, if you're expecting a very large event and you expect this artificial current to be created in your power grid, you would deliberately turn down the amount of power that you are sending to the grid. This might even involve some sort of mandatory blackout periods, for example. But by lowering that power deliberately, when this power is then created from this event with the sun, you're not breaking any transformers. Because when your transformers break, that could take sort of 2-3 weeks to fix. And that, being without power for 2-3 weeks is very different to being without power for 12 hours, for example. Or in the airline case, again, as I said, you would deviate routes away from the poles, for example. So these relative industries, they will have their own procedures, and there are government agencies that then tell these industries what to expect and when to expect it.
Great. If you are an aviation buff and in the southwestern United States, visiting the Pima Air and Space Museum has to be top of your list. Not only are there over 400 aircraft there, but there are some unique types like the Sophia Airborne Observatory that made incredible discoveries during its service with NASA, and you can tour to see what those amazing scientists did when they gazed into the night sky and turned theoretical thinking into scientific reality. Pima Air and Space Museum is open 362 days a year and has everything an aviation geek could want. So do check out www.pimaair.org for more information. And of course, if you get bored with the planes, there are tanks across the street as well. So we have technology, we have forecasting, we have, when we're talking about the technology, we're creating ourselves another problem. So the sun has its own natural phenomena.
Yep.
We've got man-made phenomena, which is space junk. So yes. I suppose the first question is, do we actually know how much stuff we have put up there? And as fabulous as it is watching all the latest launches with new rocket technology and stuff, they're putting even more up there. So yes. Do we know how much stuff is potentially junk?
It's a great question. And the two topics are actually not completely separate for reasons we can discuss. But certainly we are putting a lot of junk up there. We have the last 2-3 years, we crossed the threshold of sort of 10,000 active satellites in space. But for every sort of active satellite, there is more junk. And this varies. So we can track things in space that are around 10 centimeters or bigger. So this is a lot of stuff we can track. Again, we're tracking thousands, a couple of tens of thousands of these objects in space, we're able to track. And things smaller than this, we can't track. But you might be wondering, what is this junk? How does this get here? Why is there just junk in space? Well, a lot of it comes directly from us putting things into space, creates junk as well. So when you launch something from the ground, your payload, so your satellite is strapped to the top of a rocket. This rocket might have a few different stages. The point of this rocket is to get this satellite from the ground to space. And then when it's in space, this rocket is now junk. It's done its job, but it's still there, just floating in space. We're getting better at dealing with that now. Nowadays, it's more common for the rockets to come back. But there's a whole bunch of these rockets up in space. There is also things like, if you have water or condensation on your rocket when it launches, or a grain of sand or a piece of dust, when it's up in space, this will then come off of your rocket. It will freeze, solidify, and you'll have these tiny things floating around. And you might think, what's the problem? Why does it matter if there's a grain of sand in space? Well, in low Earth orbit, things move very, very fast. So, for example, if you're at an altitude of about 400 kilometers, this is close to where the International Space Station is, things are traveling at 17,000 miles per hour. So if you have something going this way at 17,000 miles an hour, right, this way. And then you have something, I guess not everyone can see me, but then you have something moving the opposite direction, also moving at 17,000 miles an hour. If they collide, you now have a collision of relative speeds of 30,000 miles per hour. And I can tell you at those speeds, even a grain of sand carries a lot of force. There's a very famous picture taken by British astronaut Tim Peake, actually, of the window of the International Space Station, a chip in the window. This chip, thankfully, only about a centimeter across, but they think this chip was caused by a tiny fleck of paint that came off a satellite probably decades ago, has been in orbit, and then impacted the space station and was able to chip the window, just a tiny, tiny fleck of paint. So these things, are important. And then the risk is the more things you have in space, the higher the chances of more things colliding. And then when you have more things colliding, these then break into clouds of debris, and then you have even more things in space, and you can sort of see how that could potentially create a bit of a loop.
So is that the Kessler syndrome?
So the Kessler syndrome would be the worst case scenario of this. Thankfully, we are not close to the Kessler syndrome. I believe if we take the steps that we're starting to take now, this will never happen. But the Kessler syndrome basically says you have something hits satellite, this creates a cloud of debris, then each piece of debris will then go through space. Each one of them might hit another satellite, which will create a new cloud of debris, and then things just cascade until everything in near-Earth orbit is debris, right? Everything, and what this means, if everything is this cloud of debris, we essentially build a prison around the Earth, because you can't put anything into space. You can't put satellites into space. So weather satellites, science telescopes, military satellites, you can't put them in space anymore because there's a cloud of debris in the way. And not only that, but you can't leave Earth to go to the moon or Mars or wherever because of this cage that you've built around us. That's sort of the worst case scenario that hopefully we will never reach.
So I guess from reading your book, we have options to clean things up. And I guess one of them is to deorbit them, let them burn up in the atmosphere. But there's other, as we were saying before, with planning, with solar flares and the like, tracking, avoidance, changing orbits, I guess is there. But what are the sort of options that you sort of alluded to that we're taking to not get to Kessler's nightmare of trapping ourselves on Earth underneath a big sheen of stuff?
So as you say, there are different steps. So the first thing we can do is avoid collisions. So there have been some famous examples in history. There was a test by the USA, I think in the 70s or the 80s, and in the sort of early 2000s, China did the same thing. They're called Star Wars tests. That's the official name of them, Star Wars tests. And basically these were military tests to demonstrate military capability of blowing up satellites. And these were both done sort of under the guise of, I have this old defunct weather satellite. Let's take it out of orbit. We'll blow it up. Really, it's a show of force, right? So the first thing, stop doing that. Stop messing around. Stop deliberately blowing things up, right? That's step one. And I think governments and countries have sort of appreciated that. The risk of doing that is quite high. The second thing that
just thinking there's that famous picture of the F-15 launching the anti-satellite missile from the last, there's the 85, I think it was. Yeah,
that's the one.
I'll try to drop that in because it is a really cool picture, but we don't like that.
If you look at a graph of like the amount of objects being tracked in space with time, there are clear spikes in this graph, where one object has now become 1,000 objects from these tests. You can actually pin down the tests just to looking at a graph of the amount of things in space. So bad. But a cool picture.
Yes.
Where was I? So the other thing we can do, or the next best thing, is to try and avoid collisions between satellites. So we track, as I mentioned, things from the ground. We can use radar, we can use lasers, so we can track the positions of these satellites. And if it looks like a piece of sort of uncontrollable junk, maybe this is an old satellite that has run out of fuel, if this is about to hit an active satellite, satellites will carry propellant on board, where if it looks like they're going to collide, they will physically move out of the way. And SpaceX, for example, they have thousands of these Starlink satellites, and they do many of these maneuvers every day. So things are always moving around. And this is actually a bigger problem near times when activity on the sun is high. So I mentioned to you before, these solar flares, the light sort of hits the upper atmosphere of the Earth, causes it to heat up. This actually causes a little bit the upper atmosphere of Earth to expand just a little tiny bit. So now satellites that are in low Earth orbit that maybe were flying through a vacuum, as a solar flare happens, the atmosphere expands. Now there's a tiny bit of air resistance that wasn't there before. And when this happens, satellites sort of feel that sort of drag, that friction, and they slow down a little bit. So when you have a large solar flare, you're tracking everything, a flare happens, everything moves and is no longer where it should have been. And it can take several days to sort of retrack and reposition everything and learn where everything is. And it's during those periods that collisions are quite common, just because everything is moving around more chaotically. And satellites can actually deorbit when that happens as well. They can actually lose enough speed, they lose altitude enough that they can burn up in the atmosphere. Another preventative thing that we can do is we can be sort of proactive in planning sort of an end-of-life plan for your satellite. So when your satellite reaches the end of its life, when it's about to run out of propellant, don't just leave it there to become junk that could collide into something else. Deorbit it. So if you are in low Earth orbit, it is now official United Nations recommendations. And again, these are recommendations, not laws, because how do you police this across, different nations and private companies, right? But it's a recommendation that thankfully companies and countries seem to be following. But yeah, if you're in low Earth orbit, deorbit, burn up. And if you're out sort of geostationary orbit, at sort of the reaches of Earth's orbit, go the other way. So to just go out into space and just hang out there.
And you do have a futuristic option in your book, which I just absolutely adored. Which, I know I literally called Space Bin Men, but that's kind of what we're talking about when it's catch and remove system.
Certainly. The final part, or the final option, that seems like science fiction, but is not. There have already been tests. So this hasn't been done at scale yet, but there have been tests from the UK Space Agency, the European Space Agency, is to physically go up there and remove the junk. And different groups are experimenting with different methods. You could try like a net to sweep up with some junk. You could try like a little harpoon or a giant magnet to scoop up some of these things. But my favorite one is the idea of basically like an arcade claw, right? So there's a big piece of space junk. This is for removing larger objects. You essentially you reach up, you grab it like an arcade claw, and then you decelerate, so you lose altitude, and then you burn up together in the atmosphere. So it's a suicide mission for the satellite, right? You're both burning up together, but this is to remove like the very largest, biggest objects that are flying around up there that pose a bit of a risk. There's stuff up there. There's a European Space Agency satellite, an old weather satellite called Envisat, and this is a big weather satellite the size of a bus, and it lost communication. So it's just up there, and that's the biggest piece of junk we think, basically a bus-sized piece of metal just flying around uncontrollably. So things like that would be fantastic to get out of the way.
So kind of like in Bond, You Only Live Twice with Blofeld's sort of space capture sort of thing.
Niche reference, but we'll go for it.
There we go, Bond songs. All right, let's talk about our last one, which is space rocks. And I guess really not all rocks in space are equal, are they?
Yeah, there's a bunch of different stuff in space, right? Space is not empty. So there are large asteroids, there are large comets. These leave debris as they travel throughout the solar system. So comets, you might see, they have this really famous tail, and this leaves a tail sort of throughout the solar system, and such that it leaves this tail sort of stays in place. Then every year, for example, the Earth can orbit and move into this cloud of debris, and that is how we get meteor showers. So meteor showers, you might be feeling, there's some famous ones, the Geminids, for example, the Leonids. These happen around the same time every year, not because there are meteors actually flying into the Earth, but because Earth is flying through this sort of tail of debris. But most of those meteors that you see, if you've ever seen like a shooting star, that's sort of a meteor, these are tiny. We're talking sort of the maximum the size of your fingernail, but most of them sort of the grains of sand. And these cause these huge streaks of light in the sky. But these aren't really concerns. The ones that we're concerned about are sort of these larger sort of, source objects, your asteroids and comets. And we care about them if they are big enough. Typically, if they're above 100 meters, we pay attention to them. And also if their orbits come close to the Earth. So if something is above 100 meters and sort of its orbit it comes within sort of 30% of our own orbit from the sun, we would classify this as a potentially hazardous object. And potentially hazardous is very lenient. We're tracking a lot of these that probably will never be hazardous, but it's good to sort of pay attention and watch them. And these are the ones that, we are devoting time and resources to track and monitor and things like that.
So I know people's minds are immediately going to Armageddon here, and that sort of idea of a huge object coming straight to Earth. There's the line in that film, which is,
Dan, we didn't see this thing coming.
Well, our object collision budget's $1 million. That allows us to track about 3% of the sky. And begging your pardon, sir, but it's a big-ass sky.
What is the sort of capture? This is, I didn't prep you with this one. Do we know what sort of the capture rate is for the stuff in our local vicinity that we can keep an eye on?
Yeah, so it depends a lot on where they are coming from. So stuff that is sort of coming from the darkness of space, it's fairly easy to track these. We do a very good job. But things that come sort of from behind the sun is a lot more difficult. You're sort of blinded by this light. I'll use an example. I think this was the beginning of 2024. There was a new asteroid that was discovered. Maybe this might have even been 2025. But there was a new asteroid that was discovered, and it was coming, or it was observed that it was designated as having a 3% probability of hitting Earth in like 7 years' time or something. Now, this asteroid was not big enough to sort of cause, dinosaur level event. That's not what we're talking about here. But it could cause, if it landed in an urban area, could sort of flatten a city metropolitan sized area. So again, most of the Earth is not habited, so maybe that would be okay. But if it landed in the ocean, you could sort of get sort of some tsunami effects. If it lands on land, again, you don't want anyone to be living there. And this was discovered, and we devoted a bunch of resources to try and understand how big is this thing, where is it coming from, and then as you get more data with coming days, you're then able to sort of narrow down your certainty of what actually is going to happen. And now we think it's almost certain, very close to 100% likely it will not hit the Earth, which is fantastic. It might still hit the moon. I think this is like 2032. It might hit the moon or something, which will be cool. But this is a demonstration, I think, of the process. You find something that potentially could be troublesome, so you devote resources to learn more about it. In this case, we got lucky. It's not going to be a problem, but if it had been, you'd be able to pin down that trajectory and even sort of narrow down where on the Earth that actually might impact.
Yeah, you said might hit the moon. When's Artemis 4?
Yeah, well, maybe if things get delayed, that could be around then. But again, the moon is very big, so you'd be very unlucky if, like, the only 4 people on the moon were living in the exact spot that a meteorite hit the moon. That would be bad luck.
I think, again, when we talk about sort of the deep impact, I'm pulling 90s movie references out of my ass left, right, and center here. So sorry for people that didn't see this stuff at the cinema. I'm old and it sticks in my head. When something big, to use a scientific term, hits the Earth, lots of different things. You mentioned, like, if it's in the sea, tsunamis, things like that. We were out in Arizona the other year. We went to the Barringer Crater, which is fantastic. Everybody should go there. It's wild and possibly the most windy place I've ever been in my life.
Sure. Yep.
But those sorts of events, and we think of the ones you have in your book as well for the Russian ones, when that happens, what is the impact to the Earth? Well, you said tsunamis. I'm guessing we're also talking weather changes and things like that.
Yeah, so there's a sliding scale. There's a scale that sort of measures these impacts called the Torino scale. This goes from 0 to 10 and talks about these sort of larger impacts. And the largest impact, or the largest number on this scale, so 10, is not dinosaur level, right? But the sort of type of impact we might expect maybe once or twice every million years, for example. And these are levels that can cause basically climatic change.
Please tell me an extinction level event is 11.
Yeah, I don't. The scale just doesn't go that high. Formally, the scale does not go that high.
Because you would hope that there's a few Spinal Tap fans that just go, yeah, we'll turn it up to 11. If it's 11, we're all dead, sort of thing.
Yeah. So it sort of camps at 10, and this level, it's at a level that can cause a change in the climate. So a big impact, or meteor hits, let's say the Arizona desert, for example, right? For hundreds of miles, you could flatten everything. That shockwave could go out, flatten everything around you. Trees will be flattened. There was an event that you mentioned in Siberia just over 100 years ago, and this flattened, again, a city-sized area of forest, potentially even causing the death of 3 foresters within that time. And even that was, I think, a 7 or an 8 on this scale. But on these larger events, you hit the ground, shockwave, but the bigger problem is as that process causes dust to get kicked up in the air. And when you have dust entering the atmosphere, you think it would just fall back down again. But if dust and dirt gets high up enough, it doesn't fall down. It gets caught in sort of global wind streams, and that can actually cause a change in climate. You can basically reduce the amount of sunlight that hits the ground, and that can cause temperatures to drop. There are obviously different extremities of this. So we think the event that wiped out the dinosaurs, for example, 67 million years ago or so, those dinosaurs were probably not killed by a shock wave or an explosion or what you imagine it to be, but they were probably killed in the decades or even centuries that followed due to the climate just cooling down, everything being cold, food not growing. That's why sort of smaller mammals that we evolved from, right, were able to survive in those colder sort of conditions, but sort of larger animals, cold-blooded animals, right, were not able to. So that's a very extreme example, but every million years or so, we might expect something to sort of change the climate in some way, and that's sort of this largest level. But there's been nothing like that in sort of human recorded history,
and hopefully nothing for a long, long time to come. So, yeah, that's just me being selfish. But there we go. This has been fascinating, and the book is beautiful. Your explanation, along with a lot of the imagery. There it is. Yeah, we'll twin. There we go.
Oh yeah, there we go.
There we go. Super. Is for an idiot like me in the sections I've had a look at and we've talked about, really, really well done. And yeah, thank you for taking the time to chat through this as well. You said paperback is due next year if people are paperback people, and hopefully a few tweaks.
Yeah, we're still finalizing plans for that, but there will be a paperback version. For now, it's sort of this hardback version, almost like a smaller coffee table size. It's not sort of full size, but yeah, a nice little book. As you say, I don't assume any prior knowledge. I mean, it's not an academic textbook or anything like this. But if you are interested in space or not interested in space and want to know how things in space can be relevant to you, even as someone who doesn't care in space, then I can recommend it. And I think probably maybe too advanced for like small children. But if you're sort of at secondary school, then yeah, or know anyone in secondary school, this would definitely be suitable for them.
And just general space geeks will love it. Certainly. As well. I'm going to be delving into it even more. And when I told my wife that the Behringer Crater was in it, she said she wanted to have a read. So there we go. Perfect. You've got her on side already. So if people want to follow you, check out your solar imagery, where can they do that, Ryan?
Yeah, probably the best way is just go onto my website. So it's ryanjfrench.com, J being the middle initial. All my socials are listed there. So I'm on Instagram, TikTok, Twitter, Facebook, all of the way. And and you can find all of those, and I post similar content everywhere.
Superb. Links will be in the description below. This has been a delight. Thank you for spending a bit of your morning and my evening with us, Ryan. I cannot thank Ryan enough for joining us on the Aviation Show to discuss his book, Space Hazards, Asteroids, Solar Flares and Cosmic Threats, which is out now, and of course you can get it via our bookshop.org affiliate links in the description below. Next week we stay on the space theme as we chat to the director of a new documentary entitled Beyond Blue Sky, The Untold Story of the First Private Astronauts, which is all about Burt Rutan and Scaled Composites winning the X Prize in 2004, and we're also joined by Matt Steinmetz, who is the lead engineer on Spaceship One and also flew in the back seat of White Knight 1 on all the X Prize flights. So be sure to like and subscribe so that you don't miss out on this fascinating discussion about a truly incredible endeavour by one of the legends of aerospace. I'd like to say thanks to all of our fantastic supporters over on Patreon. If you head over to our Patreon page, you can join the fun from just £3 a month, plus a bit of VAT, get your name in these very credits, and get all the episodes ad-free and early as soon as I get the edit finished.